want to start today with a bit of a paradox. Imagine you own a house.
Yeah. Okay.
And you've bought the best locks money can buy. Steel bars on the windows, a high-tech security system.
It sounds like a fortress. I'd feel pretty secure.
You'd think.
Mm-hmm.
But then you come home and your safe is wide open. Valuables are gone.
Oh, no.
And here's the kicker. The security cameras show the burglar didn't bring a single tool inside. They walked in completely empty-handed.
So how did they get into the safe?
They used your stuff. They went into your kitchen, grabbed a spoon, a rubber band from a junk drawer, maybe a battery out of the TV remote.
Oh, wow.
And they MacGyvered a way to crack the safe right there on your counter. They didn't bring anything malicious in. They just recycled what you already had.
That is the perfect analogy for what we are diving into today. It's terrifying, but it's also really elegant.
It is.
We're looking at a stack of notes, some technical docs, and walkthroughs on return-oriented programming, or, ROP.
Digital recycling, but with a malicious twist.
Exactly. This deep dive is all about understanding a fundamental shift in how hacking works. We're going to look at how attackers get past modern defenses.
Big, scary terms like executable space protection and code signing.
Right. And the scary part is they aren't writing new viruses, they aren't injecting bad code, they are hijacking a program's own honest, hardworking code to do their bidding.
We have a lot of ground to cover. We've got the theory, which is fascinating, but also some hands-on walkthroughs of C programs, a set of demos called vuln.c.
And we have notes on the heavy machinery, tools like GDB PETA and Pduin tools.
But before we get to all that, we have to understand the environment. I mean, why did attackers even start recycling code? Why go through all this trouble?
It's always necessity, right? To understand ROP, you have to understand what it replaced. The source material calls ROP the advanced version of the classic stack smash.
The stack smash. That sounds violent. Like a wrestling move from the 90s.
It was blunt force, yeah, very much like a wrestling move. Back in the day, if you found a buffer overflow...
A place where you could type in more data than the program expected.
Exactly. You could just overwrite the memory stack. And the key thing was you could write your own code into that overflowed space.
Right. This is the shellcode era. I send a server a request that's too long, and hidden inside that extra data is a tiny program that says, give me a command prompt.
And the computer would just happily execute it. The stack was like the Wild West. You could store data there, you could run code there, nobody cared.
But our sources say that doesn't really work anymore. That door's been locked, so it changed.
Well, defenders got smart. They introduced a defense called NX. It stands for no execute.
No execute.
It's kind of like modern zoning laws, but for computer memory.
Zoning laws. That's an interesting way to put it.
Yeah. The operating system looks at the stack and says, this area here, this is for data storage only, residential only, no business is allowed.
And if the computer tries to execute code from there,
the CPU throws a flag, kills the program immediately.
The source material actually points this out in the demo setup. It mentions they had to remove a compiler switch as the stack. In the real world, the stack defaults to RW read and write only.
Correct. No X and no execute. So as an attacker, I can still crash your program. I can still write jump to the stack. But if I try to smuggle in my own shellcode,
the CPU just ignores it. It won't run.
It's like trying to start a fire with wet wood. You have the fuel, but you've got no spark.
So the old method is dead. You can't bring your own weapon.
Oh.
Which brings us right back to our MacGyver burglar. If you can't bring new code in,
you have to use the code that is already there. And this is the core aha moment of return-oriented programming.
The computer's memory is already full of code.
Full of it. The operating system, the libraries, the program itself, it's all valid, executable code that the CPU trusts.
So the attacker thinks, why write my own instructions when I can just trick the computer into running the ones it already has?
Exactly. And this is where we get the term gadgets.
I love this term. But we are talking about, like, smartwatches or James Bond pens here. What is a gadget in this context?
A gadget is just a tiny snippet of instructions that's already inside the program's memory.
How tiny?
Usually very short, maybe 2 or 3 instructions. Something trivial like move number A to location B.
And these are just sitting around?
Everywhere. They're the tail ends of functions, little cleanup tasks. But the key feature, the thing that makes it a gadget, is that it ends with one specific instruction. RET.
Return. That's the R in ROP.
Right. The RET instruction is the crucial hinge. It tells the processor, I'm done here, now go back to the stack, grab the very next address you see, and jump to it.
So by controlling the stack, the attacker controls where that RET instruction jumps to next.
You got it. If you can line up a bunch of these gadget addresses on the stack, you can make the processor jump from A to B to C.
It executes gadget A, hits RET, jumps to your address for gadget B, executes that, hits RET, and so on.
It's like cutting letters out of a magazine to write a ransom note. The magazine editor never intended for those words to form a threat, but you've rearranged their trusted content to say something malicious.
That is a terrifyingly good analogy. Okay, so we're stitching together existing code. Our notes say the most common source of these letters is something called the return to lib attack.
Yeah, this is usually step one in learning ROP. Lib is the standard C library.
It's loaded by basically every program on a Linux system.
It is. It's the encyclopedia. It has all the standard functions for, opening files, printing to the screen, and most importantly, executing system commands.
So instead of writing your own code to open a shell,
You just find the page in the encyclopedia where the system function already lives. It's there. It's trusted. Why reinvent the wheel?
let's look at the demo in the source. ctf-demonstrok1 vol.n.c. This seems like a practice target designed specifically to teach this.
It is, and it's a pretty generous one. When this program starts, it actually prints out the memory addresses of system, printf, and main.
That's super handy. In the real world, you usually have to hunt for those because of things like ASLR, which randomizes everything.
Right, but for this lesson, the source gives us the map coordinates. The goal is simple. Hijack the control flow. When the current function finishes, instead of going back where it should, we want it to jump straight to the system function.
Okay, walk me through it. Step one in these breakdowns is always the same, isn't it? Break things.
Always. Step one is to crash the program. You run it with longer data. Just flood the input buffer with a ton of characters.
And when they do that, the notes highlight a very specific value that shows up in the EIP.
EIP being the instruction pointer.
The "you are here" arrow for the CPU,
And the value was 414144141.
which is hex code for triple OA.
That's the proof. It confirms we control the instruction pointer. We successfully flooded the buffer and overwrote the return address with our A's.
And if we can put A's there, we can put any memory address there.
But just crashing it isn't enough. You need precision. You have to know exactly where in that flood of A's the return address actually is. And this is where a tool like GDB-PETA comes in. It's a debugger that helps you calculate the offset.
The offset. The distance from the start of our input to the exact spot that controls the CPU.
And in this specific demo, GDB-PETA tells us the offset is exactly 44 bytes.
Okay, so the recipe is 44 bytes of absolute junk, followed immediately by the address we want the computer to jump to.
Correct. So we build a payload, 44 bytes of junk, then the address of system.
But wait a second, system is a function. It needs an argument. You can't just tell it to run system, it'll ask system what? We want it to run binch to get a command shell.
And this is the tricky part. You have to find the string binch already existing somewhere in memory.
Back to the magazine search.
Luckily, libvic is huge. It almost always contains that string somewhere inside it. GDB-PETA has a find command that just locates it for us.
So the final payload for what the notes call exploit A is 44 bytes of padding, the address of system, a fake return address placeholder, and finally the address of that binge string.
You nailed it. The function returns, it jumps to system. System looks at the stack for its argument, sees the address for binch, and executes it. Boom. You have a root shell.
That's so satisfying. But there was a second one, exploit B, which I thought was hilarious. It wasn't about getting a shell at all.
No, it was about ego. The program has a password check. Exploit B is just about forcing the program to print password OK, even if you have no idea what the password is.
I reject your reality and substitute my own. It's just hacking for the sake of being right.
The mechanics are identical, though. They use the debugger to find the memory address where that password OK text was stored. Then they overwrite the return address to point to the print function with that string's address as the argument.
So the program fails the password check, but then we hijack the return to make it say, actually, you know what, it was fine.
Exactly. It's
Yeah.
a great example of bending the program's behavior without ever touching its actual code.
That's very cool, but these are single-shot attacks. We call one function system or print, and then the program probably just crashes.
Yes, that's the limitation. Once that hijack function finishes, the stack is a mess, and the program usually just segfaults. It dies.
But what if I need to do more? What if I want to open a socket, then connect back to my server, then launch a shell? I need to call 3 or 4 functions in a row.
Now we're entering the true art form. This is where return-oriented programming really earns its name. We need to build a chain.
A RP chain. Sounds like we're building a machine.
We are. The problem with chaining functions is the mess they leave behind. When you call, say, functio arg1. That argument, arg1, gets left on the stack.
It's like dirty dishes. You can't serve the next course until you clear the table.
Perfect analogy. If the next function tries to run, it might see that old argument and think it's a return address, and then everything just crashes. We need a way to clean the stack between function calls.
And the sources introduce a specific gadget for this job, the popret.
The popret is our busboy.
Okay, break that down. What does pop actually do?
In assembly, POP just means take the top item off the stack and put it in a register. Essentially, it removes one item from the stack.
And RET, we know, means execute the next thing on the stack.
So here's the dance. We arrange our payload like this: address of function 1, then the address of a popret gadget, then the argument for function 1, and finally the address of function 2.
Whoa, okay, that's a lot of moving parts. Walk me through that.
Sure. First, the CPU jumps to function 1, it does its job, it hits return. The return address it sees is our popret gadget.
So it jumps to the gadget.
The gadget runs POP. That removes the old argument from the stack. It clears the dirty dish. Then the gadget runs RET. The CPU looks at the stack, and because we just cleared off the old junk, the very next thing waiting is
The address of function 2.
exactly. We have successfully bussed the table and seated the next guest.
That is incredibly clever. You're weaving these little cleanup instructions in between your actual commands just to keep the machine running?
And it lets you chain an infinite number of functions. You're literally programming the machine instruction by instruction using scraps of its own code.
And you don't have to find these gadgets manually, right? The notes mention a tool called ROP.
Oh, good Lord, no. That would be insanity. ROP scans the binary file for you, and it spits out a list of every potential gadget it finds.
It's like a shopping catalog. Need a popper wook. Read, do you have one in stock?
And ROP says, yep, got one right here at address 0 by 0804. You just copy-paste that address into your chain. It makes building these things almost like using Legos.
Speaking of automating, the source material then pivots to the modern way of doing this. Because counting 44 A's and typing hex addresses, you're going to make a typo.
Enter PwnTools.
Sounds like a box of toys for hackers.
It's the industry standard for this stuff.
Yeah.
PwnTools is a Python library that handles all the gritty, annoying details for you.
The source walks through using it on ctf-demonstrap2volen.c. What does PwnTools give us that, say, a simple script can't?
Sanity and dynamic capability. With PurnTools, you don't manually type A 44 times. You tell it to generate a special pattern. Then, when the program crashes, you feed the crash value back to PwnTools, and it calculates the offset for you automatically.
So it does the math.
It does the math, and it handles the connections. The notes mention that netcat-loop.sh script. PurnTools can switch seamlessly between hacking a local file and a remote server. You just change one line in your Python script from process to remote.
That's powerful. It really standardizes the attack. There was a weird note in there about ASLR again. Address space layout randomization.
Right, the thing that scrambles memory addresses every time you run the program.
The source note says something like, the exploit is reliable enough to work even if ASLR is turned off, so let's turn ASLR off.
Yeah, that phrasing is a bit for the tutorial. They turn it off to make learning easier, but what they're hinting at is that PwnTools lets you build exploits that can adapt to ASLR. If you can leak just one memory address while the program is running, say, the address of printfp_ontools can calculate where everything else in that library is relative to that one known point.
I see. So if you know where the library starts, you know the distance to system is always the same.
Exactly. PwnTools does that base plus offset calculation instantly. So ASLR can move the library to a new neighborhood, but the layout of the house stays the same.
So the workflow becomes, write a Python script, let PwnTools build the payload and handle the networking. You just hit enter and watch the shell pop up.
It turns a manual, error-prone surgical procedure into a push-button attack.
We've really gone from smashing the stack, which was just brute force, to this elegant, almost artistic method of ROP, surfing through lib chaining gadgets.
It really is a paradigm shift, and it teaches us something pretty profound about computer security.
What's the main takeaway for you?
That verifying the source of the code just isn't enough. We spent years making sure bad actors couldn't put their own bad code on our machines. We checked signatures, we locked down permissions.
But ROP proved you don't need bad code to do bad things.
You just need to arrange the good code in a bad order. It really highlights the importance of what we now call control flow integrity.
It's not just about, is this code trusted? It's, is this execution path valid?
Precisely. You have to look at the behavior, not just the bytes.
You know, looking at the exercises at the end of the source material, it sparked a weird thought for me.
Where's that?
When we do a ROP attack, we're executing valid instructions.
Hmm.
The CPU is running POP, RET, MOV.
Hmm.
These are all safe, standard instructions. From the OS's perspective, everything looks fine.
Right. No red flags. Everything seems legitimate.
So, does the program ever really crash? Or is it
Right.
more like it becomes a zombie?
That is a provocative way to put it.
Think about it. The original soul of the program, its intended logic, is gone. We wiped that out when we overwrote the return address.
But the body is still moving.
It's walking forward, step by step, executing instructions. From the hardware's perspective, everything is completely fine.
You're right. It hasn't crashed. It's been possessed. It's zombie walking through memory, doing things it was never meant to do, just waiting for the whispered command to hand over the keys to the kingdom.
It's deeply unsettling. It's like the program is sleepwalking into a bank robbery.
And you're the one guiding it by the hand?
Well, on that slightly creepy note, we're going to wrap up this deep dive into return-oriented programming. It's a complex topic, but hopefully the next time you hear about gadgets, you won't just think of smartphones.
You'll think of stack cleanup.
Stay curious, everyone, and check your return addresses. We'll see you in the next deep dive.